All right, good morning, everybody. My name is Richard Sandberg, and I'm the current director of the Melbourne Energy Institute, and I'm also a professor in the Department of Mechanical Engineering here at the university. I'd like to begin by acknowledgement that today we're gathered on the lands of the Wurundjeri, Woiwurrung and Boonwurrung people, who have been custodians of this land for thousands of years. I pay my respects to their elders past, present, and future. So I would like to welcome you all to this 2025 edition of the Melbourne Energy Institute Symposium. It's great to see a good number of people in the room, which I think is testament to the vitality of this community and the relevance of the work that's going to be presented today. I believe holding such events is crucial in a time where net zero has again become a hotly debated term in Australia, and I think hearing about world-leading research in the energy space hopefully will instill you with some confidence that the technologies, ideas, and talent exist to build a more sustainable energy system. Over the next 8 hours or so, we'll hear a plenary and 4 keynotes from our distinguished invited speakers, and talk from a number of talented researchers from different universities. The speakers will cover topics from across our 4 research programs. Those are power generation and transport, energy materials, heavy industries and resources, and energy systems. And additionally, we'll have posters from our PhD students that are going to be shown outside and that I hope you have time to see during the breaks. And we've chosen a new format for the symposium this year, so we're going to do all of this in a single session, which we hope is beneficial to everybody because you get the opportunity to see all the talks and don't have to choose. So I hope you like the new format. And of course, we're putting all of our speakers under pressure to talk faster because we have less time. So I encourage you to share, question, challenge, and collaborate. And I hope that you will get inspired to further advance the boundaries of knowledge in the energy space, and that you can use the breaks to form new connections and strengthen old ones. So before we get to the plenary, I'd also like to say a big thank you to our fantastic MEI team, who has put a lot of work into organizing the symposium. So I'd like to thank Franca, Anita, and Josie, who is somewhere outside. So thank you very much. And I'd also like to use this opportunity to acknowledge the leadership and vision of our previous MEI director, Professor Michael Breer, who is here, who really shaped the MEI you see today. And I'm not going to put you on the spot, Michael, but you can relax today, I guess. All right, up to the plenary. We're grateful to have Professor Eric MEI deliver the opening plenary today. Eric is Managing Director of the Future Energy Export CRC and Director of Gas Capture Technologies. His research team works closely with industry, conducting projects in hydrogen liquefaction, LNG production and decarbonisation, gas separation, CCS, and fluid property prediction. Eric was awarded Western Australia Scientist of the Year in 2021 and the Malcolm McIntosh Prize for Physical Scientist of the Year as part of the 2012 Prime Minister's Prizes for Science. In 2017, next slide. Oh, I'm sorry. In 2017, he co-established Gas Capture Technologies, a spin-out company for patented technologies to capture methane from coal mines, landfill gas, and other sources. So today, Eric will present on how LNG fundamentals are advancing the new energy technologies of liquid H2 and CO2 transport. So please welcome Eric MEI.
Good morning, and thanks very much, Richard and Franca and the team for giving me this opportunity to speak to you today about research that we've been doing for some time, but also sort of a view to the future that we're looking forward to continuing over the next few years. the CRC actually held its annual conference in May in this room, so we're somewhat familiar with Melbourne Connect, and it's a really lovely venue, and it's great to see so many colleagues, and the University of Melbourne is a core participant in the Future Energy Export CRC, and we're again really grateful for the capability that you guys bring to the CRC's offerings for research to industry. Okay, so today I'd like to talk about how the lessons that have been mastered by the world's liquefied natural gas LNG industry are absolutely critical to any new global decarbonised energy system, and also how the associated knowledge with those lessons will need to be expanded if we're going to deal with the unique properties of liquid hydrogen and liquid CO2 transport. One of the world's humanity's current grand challenges is figuring out the problem of how do we maintain a secure large-scale energy supply that underpins the sort of standards of living that we're all accustomed to and helps them to grow, whilst also reducing the amount of CO2 that's produced at the same time. And the answer to that question is often thought to be, well, maybe we should just electrify everything. We just put up some solar panels and some wind somewhere, and we'll connect it via a transmission line to where that energy is needed. And we understand that the renewable resources aren't necessarily in the same place as where the demand for the energy is, but surely we can just solve that with transmission lines. Okay. The problem with that is that transmitting energy over long distances electrically is very expensive. And what this chart is showing is, if I'm just going to get my pointer up, where are we? There we go. And I will bring this down here. Okay, so here we've got the cost in dollars per megawatt hour per 1,000 kilometres to transport as a function of the different types of ways in which you might transport that energy over that distance. And you can see that the cheapest way to transport energy is by oil. That's why oil is such an important energy storage and vector for the world. As you go up other liquids that are less energy dense, slightly increased costs, and of course there is a range associated with this. But when you get to a gaseous phase, natural gas and even hydrogen, you can see that these are factors of 5 or to 10 times cheaper than transmission by a high voltage DC pipe, transmission lines. So electrical transmission is much more expensive. So the key takeaway here is there's a rule of thumb that if you're going to move energy, moving molecules is a much cheaper way of doing it than moving electrons. And the way in which people move molecules most efficiently is to build pipelines, whether it's liquid but also gas pipelines. And so pipelines are critical technologies, are really a marvel of engineering. They allow us to access remote reserves of energy, such as these gas fields offshore Western Australia, to bring that gas up to a few 1,000 kilometres subsea to liquefied natural gas plants in Western Australia. There's also a 2,000 kilometre pipeline that goes from that site here down to Perth to provide that gas energy. And it's amazing to try and imagine a pipeline that was built or started being built in 1979, something of that scale being done today, but that's a discussion for another time. And then if you look at the United States grid of pipelines, it's even more incredible. Something like 3 million miles of pipeline infrastructure if you were to put it end to end, which is 12 times the Earth to Moon distance that really is there. So pipelines are the way in which if you can build them, and they're very cost effective when it comes to making energy transport. But when it comes to moving energy across sea, that's when these gas pipelines become more expensive than the other alternative, which is to ship the energy. Okay, and so this chart is showing, again, in terms of dollars per unit of energy, as a function of the distance between where the energy starts and where it needs to go. that by the time offshore you get to about 1,000 miles, it's cheaper to build the facilities, to liquefy, ship, and then regasify that gas in the form using LNG technology. And even on onshore pipelines, at certain distances, it becomes cheaper to, or almost as cheap to make LNG. So across oceans, shipping liquefied natural gas is the way to go if you need to move large amounts of energy around. And that has led over the last 50 to 60 years to the development of what's a very nowadays mature supply chain, the liquefied natural gas supply chain, where you basically have 4 stages. Production of the gas, it gets treated to remove impurities that are incompatible with its safe use and its long-term storage. And then it's liquefied and waits in storage systems before it's shipped to where it needs to go and then converted back into the gas phase. And as of 2024, the world's system for distributing gas from where it's available to where it's needed is again a remarkably complex system. About 25% of the world's gas is transported as liquefied natural gas, and again, the geopolitical tensions that have occurred in Europe have largely been addressed, at least in terms of energy security, through this technology. Not to mention the incredible growth and the demand for gas that occurs in Asia, particularly in Japan and China, where we see energy exports as a business opportunity. They see it as national security. So it's very important to those countries. So what has LNG supply chain got to do with a decarbonised energy system? Okay. So, well, to answer that question, let's start with the rule of thumb that moving molecules is generally much cheaper than moving electrons. Okay, and so the natural question when you apply that rule of thumb to a decarbonised energy system is, well, which molecules are we going to need to move around? And reasons that I'll explore later, hydrogen and carbon dioxide are highly likely candidates that will be needing to be moving around as part of this decarbonised energy system. But noting that we need to almost certainly transport some of this across oceans, the efficient transport of these 2 molecules can be achieved by storing them as cryogenic liquids. And therefore, what we should do is apply those lessons that have been learnt by the LNG industry about efficient transport of cryogenic liquids to the design of our new systems for distributing hydrogen and CO2. And then also identify the differences, because they're not the same. There are subtle issues that will inform our research efforts, that what new knowledge is needed to make these new distribution systems effective. So let's start with CO2. So why CO2? And so this is a chart from the Net Zero Australia project that was led by Michael Breer, and one of my favourite charts. And don't worry, Michael, I'm not going to talk about the cost of net zero. This chart is about the amount of CCS that's needed in the various scenarios. And I should say the Fenix CRC was very proud to be a supporter of both the first phase and the current phase of the Net Zero Australia project. So what this chart is showing is these are the scenarios essentially that project looked at getting to net zero by 2060 for export. So you're going to export the same amount of energy Australia currently does, but in a decarbonised way. And in those scenarios, we've essentially got 2 bookends: the constrained renewables rollout, and then this other bookend, which is full renewables rollout. Okay. The scale on this axis is in millions of tons of CO2 per year, and the world's entire current CCS level is at around 44 million tons of CO2 per year. So that's the whole world. These curves are just for Australia if we were to get to net zero. And you can see that in the case where renewables rollout is constrained, perhaps because of supply chain, and constrained still means several, a factor of 2 or 3 faster than we've ever done it before in terms of deploying renewables. But maybe land access issues and other constraints means we can't actually get rid of fossil fuels in the time scale that you might think. We need basically up to 1 gigaton per year in Australia alone to achieve net zero. But perhaps more strikingly is if we imagine that there is absolutely no constraint to how fast we can roll out renewables, and we can ban the use of fossil fuels for energy basically as fast as this rollout occurs, you'll still see that by in the peak here, we need something like 80 million tonnes per annum of CCS in this fully renewable approach to net zero. Okay, so that's almost twice what the whole world does right now, just in Australia, is required to get to net zero in this most ambitious of scenarios. So the takeaway of this chart, for me at least, is that there is no path to net zero that does not involve CCS. And that means we're going to need to transport where the CO2 is produced, whether it's from the energy, but also from the hard-to-abate sector, which is why we need, why this curve has this peak, to where it can be essentially stored geologically. And that means actually there's a flip side, a positive side of that. That's a massive economic opportunity for those, a bit like the resources that we have to produce energy. There's an opportunity for those countries with the ability to store that CO2. So countries like Japan that are importers of energy similarly don't quite have anywhere to put the CO2 that they might produce. They're going to need to continue producing it. So that's an opportunity for countries like East Timor, which have the developing economy. They have the depleted gas field. The geology of that's very well known. Why not transport the CO2 to somewhere like Timor-Leste, and then you can inject the CO2 there, if the CO2 transport challenge can be solved. So how do we transport CO2? One way is shipping. And what this diagram is indicating actually is some work that the CRC did in about 2022, which showed that the cheapest way to deliver clean hydrogen to Japan today is to ship it as LNG, crack the gas in Japan, capture the CO2, and ship it back to Australia for sequestration. And you could do that for about $2.30 per kilogram, and the carbon intensity of that hydrogen would be around 4 kilograms of CO2 per kilogram of hydrogen. So it's just on the edge of clean, but if you could make it cleaner, the cost would go up slightly. But $2 to $3 was the sort of, and again, these are desktop academic studies, so I wouldn't want to invest your superannuation in these sorts of schemes. But it's not, of all of the schemes that we've looked at for delivering clean hydrogen to Japan, the most cost effective, with the weakest technical challenge part in this closed carbon cycle being the shipping of liquid CO2. Okay, so across long oceanic distances, shipping liquid CO2 is also cheaper than transporting it by pipeline. You can, of course, transport CO2 by pipeline, and the name's just escaping me, but the CCS project in Victoria that's planned, and Nick Burke, if he was here, would kill me for forgetting, what's the name? CarbonNet, that's it. Big pipeline plan to take the CO2 out to the Bass Strait. But for this sort of distance, shipping it is very important. Okay. Now, people might know about the Norwegian project, Northern Lights, where they're going to start doing this. They're taking CO2 from Germany and from the Netherlands to Norway by pipeline, and then it's going to get shipped out to a depleted gas field offshore and injected. And the shipping that they're using is actually an existing technology. It's food grade CO2. It gets transported around as a liquid all the time. That's what's called medium pressure shipping of CO2. So here's a phase diagram, and I'm a thermodynamicist, so I love phase diagrams. Here we have in log scale of pressure and in temperature in Celsius, the phase behavior of pure CO2, and these colored areas are essentially the domains under which the different transport occurs. So if you're in a pipeline, you're up here at high temperatures and high pressures. But if you're shipping it or even trucking it around, you tend to work at about minus 20 degrees Celsius, where the pressure of the CO2 is about 20 bar. Okay? Now, this medium pressure, which the world's food industry has sort of standardized, is fine if you're doing volumes of up to a few thousand cubic meters, and that's what the Northern Lights project is doing. But the pressure vessel that you need kind of limits the volume you can actually store on the ship. And if you're going to be bringing economically CO2 back from somewhere like Japan to Australia, you need a much lower pressure vessel rating to enable 10, 50,000 cubic, 100,000 cubic meters of liquid to be on that ship, which is so-called low pressure regime. Okay, so that means if you're at about 8 bar, that means you're down at about minus 50 Celsius. Okay, what's the problem? Well, it's a bit difficult to see perhaps, but you're very close to that solidification line. So unlike LNG, where you've got 30 or 40 degrees for the freezing point of the methane, for liquid CO2, if you want to get to that condition where you can ship it at relatively low pressure, you might have operability issues when it comes to the risk of forming solids. Okay, another issue that will be important is that CO2 ain't CO2, all right? So no one wants to take a waste product and purify it to the levels that the food industry demands when we're making beverages so that it can be injected into the ground. And the more you insist on high purity CO2 for CCS applications, the less likely it is that you will the cost of the CCS will go up, okay? So what this diagram is showing is a projection by Bloomberg around the various sources of the CO2. Right now, CCS is using CO2 that's usually captured from gas production. But going forward, if people, as we decarbonize the hard-to-abate sector, we produce blue hydrogen and the like, there's going to be a range of different sources, which means a range of different impurities are going to be present in that CO2. And how so the concentration for, or the composition, if you like, of this lower purity CO2 is still 96% CO2 nearly, but you've got a few percent of these lighter inerts and ppm levels, and this small variation of composition associated with the purity that is inevitable from these different sources, it causes a lot of technical issues. Okay, so one of them is to do again with the phase behavior. In the top picture here, we've got the phase diagram corresponding to this high purity CO2, and you've got a very small region in the temperature pressure plane between where it's a liquid, which is easy to transport, and where it's a gas. So ship transport in that case is still within that domain of a single phase liquid. But when you bring in these impurities, and again, only a couple of percent of nitrogen and methane and hydrogen and the like, you'll get a much greatly increased phase boundary. And in fact, although I've shown those phase boundaries, the exact location of them is not super well known. So an active area of research is mapping out the phase behavior even of these impure CO2 mixtures, not to mention the sort of potential for acid formation that can occur from some of those impurities also that are listed there in the CO2. When it comes to shipping the liquids, let's say we've dealt with that impurity issue, then we've got to actually design the ships to carry the cryogenic liquid. Cryogenic liquids boil off. When they boil off, you've got to do something with the gas. And what the LNG industry does is it puts compressors and heat exchangers to make a sort of a reliquefaction system on board those carriers. The question is, how big do you need those boil-off gas compressors to be? You don't want to make them too big because they're very expensive bits of equipment. You don't want to make them too small because then you won't be able to deal with it. It turns out that although this sounds like a relatively simple chemical engineering problem, it's highly empirical in the industry. The people literally use charts to figure out, well, I've got this tank and this level and this pressure, this will be the boil-off rate. So we've done some research over the years to deal with this complex scale-dependent process to try and come up with more fundamental models of boil-off gas. So a photograph from the laboratory, and this is some data for LNG, where we're measuring the temperature distribution in a liquefied in LNG down there as a function of time. So we're letting it heat up. The liquid surface is here in terms of its depth. And you can see that what happens is you get an increase in stratification with time, and then as you hit the sort of relief pressure, it homogenizes. But what was nice about this is we could take the model that we built for LNG and then apply it in a purely predictive way to predict what will be the sort of boil-off rates, pressurization times, and relief rates for liquid CO2 predictions. And without any adjustment of any parameters, the job it did was pretty good. Now there's still further work to do there, and we're continuing to do so. But again, by taking the models that are developed for LNG and applying them, you can rapidly use that to figure out, to try and size the sort of compressors that you might need in a liquid CO2 transport system. So now I want to move to the other molecule that I mentioned, which was hydrogen. And you can see why the hydrogen, this is a hydrogen value chain here. It's got a lot in common with an LNG supply chain. You've got the production. Here we're generating it by electrolysis, but then you need to store it. And that's the big challenge with hydrogen, is its energy density as a gas is terrible. So we need to, one way to deal with that is to convert it to a liquid phase, then transport it and use it. So it's highly analogous to that LNG supply chain, particularly if we're talking about liquid hydrogen. What lessons can we draw from the LNG sector to establish this future supply chain? Well, I said before, the LNG supply chain, which involves cryogenic liquefaction, is highly mature. So you have to cool the gas down to -160 C. That's a heat exchanger that they typically use for a large-scale LNG plant. A bundle of pipes, which basically gets sprayed by a refrigerant on the outside to cool the gas down. What could go wrong? Okay. Well, here is some operating data from a liquefied natural gas plant in Qatar around 2014. And the chart is basically on the right axis, you've got the pressure drop across this cryogenic heat exchanger in red, whereas this axis in the black curve is the impurity level of heavy hydrocarbons, C5+, in mole percent. So we're at under 1,000 part per million here. This is the specification. And you can see that for most of the year, everything was fine. You get this natural sort of variation in the feed to the cryogenic heat exchanger. They had a planned shutdown, they restarted, and then very briefly they got a spike of heavy hydrocarbon carrying over, if you like, into that LNG heat exchanger. And then after that, for the next 3 months, the pressure drop across the heat exchanger continued to rise until around December, where they basically concluded they had to shut the plant down. And so this is analogous to the problem of eating too many fries and chips and the like. You're building up deposits in your arteries. The pump can no longer push it around too long. So avoiding, what we're basically showing there is a signature of something like a heart attack for an LNG plant. So work we did with the industry was to get to the bottom of that, built high pressure cells that could be observed by a microscope, and we can zoom in on a cold spot in that system with the microscope, and that's looking down. It's full of methane with a little bit of an impurity called benzene there, and as we cool, you can see that plaque starting to come out of solution. So essentially what we're doing is mapping out, again, this is data that the industry had a lot of uncertainty around, and engineers are really good at dealing with uncertainty. They just have bigger margins, but that costs money. So essentially we're mapping out that boundary where the solids come out of solution, so that we can more precisely target and understand exactly what went wrong in this plant example. Okay, so now we're going to take that lesson and we're going to apply it to liquid hydrogen. Okay, and if you think LNG is a massive engineering challenge, then liquid hydrogen is almost an insane one. The reason is that you have to cool it about 90 degrees lower in temperature, and you spend about 7 times more energy, and that amounts to about 30% of the energy that's in the hydrogen gets used in essentially liquefying it. Still, probably, arguably, one of the most practical or cost-effective ways to store hydrogen. So that tells you something. And Here, this schematic here shows you roughly how it gets done. You take your hydrogen feed, you compress it, then you basically send it through a heat exchanger, which cools it down. It goes. I'll talk a little bit more about the details of this heat exchanger here, but there's a catalyst involved. It goes into the separator, and then you form your liquid hydrogen. And again, you have to deal with the boil-off gas problem. So everything that I said about CO2 boil-off is also applicable to liquid hydrogen. But I'm going to focus on this part of the cycle here. So you've got this impurity risk freeze out again, and now it's not just freeze out in the heat exchanger, it's freeze out on the catalyst in the heat exchanger. So how much impurity can we tolerate in liquid hydrogen? So what's the likely impurity? Well, nitrogen is ubiquitous. So you go and look at the data that exists, and NASA has been doing this also for 60 years, but they never cared about the cost, right? So that's why this is an actual engineering challenge, because we need to get this more reliable and cheaper. And if you look at the data, again, this is a log scale for the solubility of nitrogen from different authors measuring as a function of temperature. And there's an amazing amount of scatter. You look at that data and you conclude no one knows what the solubility of nitrogen in hydrogen is as a function of temperature. Okay, so we set about and we built the similar apparatus based on a microscope and a high pressure cell that allows us to actually see when the solids come out of solution. And we have generated new results for part per million solubility of this impurity in hydrogen. And so this is a diagram showing pressure, temperature, space, where solids start forming for different concentrations. So the untuned model that engineers would normally use is this sort of turquoise color here for 100 ppm, and the data actually are well inside it. And at 50 ppm of nitrogen, again, the data are much further inside the phase boundary, okay? Plotting it in a different way, shown here as a function of temperature and the solubility limit, and we've got data that are up here, but what's important is that these sorts of data allow us to identify which of the results in the literature existing are trustable and which aren't. And as a result of that, we were able to show that nitrogen is about 10 times less soluble in liquid hydrogen than previously thought. Okay, so that's an issue that the industry will need to deal with. The other thing that I think is cool about liquid hydrogen is that this is one of the few examples in the world where quantum mechanics actually matters at an industrial scale. And the reason I say that is that hydrogen is actually a mixture. It's a mixture of two quantum mechanical states of the molecule, known as ortho, which is a higher energy state where the two nuclear spins are aligned, and para, where they're oppositely aligned, and that's a lower energy state. Okay, so in terms of their angular momentum, these two things are different. And at equilibrium, thermodynamics causes the molecules to want to be arranged in different ratios. So at room temperature and above, basically, 75% of the molecules are in that ortho hydrogen state. But at liquid hydrogen temperatures, which is only 20 Kelvin, they much prefer, equilibrium requires them ultimately to be in 99.8% in that low energy state. The problem with this is that the conversion, in fact, is forbidden by quantum mechanics for an isolated molecule. So in a real system, it happens very slowly. Literally, you can watch this happen over days and weeks. But the real kicker is that the heat of conversion, the energy that gets released as that reaction occurs slowly, is actually more than the energy required to boil off the gas. So you can spend all that energy liquefying your normal hydrogen, and you wait a few days and half of it will boil off, and you will have wasted it because of that quantum mechanic effect. So that's why they have to use catalysts, and they basically put them inside the heat exchangers because these catalysts, which are essentially an iron oxide powder, make that transition very fast. So the conversion occurs on the sort of residence time scale of the gas flowing through the heat exchanger. The heat can be taken away by the refrigerant, and you can avoid that problem of the ortho-para conversion happening later. But of course, catalysts are even more susceptible to impurities than perhaps would be the case in LNG. So it's not just about blockage, now it's about deactivation of that catalyst and its effect of the impurities on those ortho-para conversion rates. So we've spent a few years building systems that allow us to study these in depth. And one of our systems is shown here, where we have a reactor and we have various sensors that allow us to measure and see what quantum state the various hydrogen molecules are in. So here's a Raman spectrum where you can see that at this low temperature there's more para-hydrogen than there is ortho-hydrogen. Okay? And so this allows us to test new materials, and we're working with industry partners to do that, but also to check how impurities will affect the performance, and also what about regeneration of that catalyst. Okay, and here's some data that we took where we deliberately have about 21 parts per million of water in the hydrogen that's flowing through that catalyst bed. And if you just look at the differential pressure across the bed for about 24 hours, there's no problem. But then you start to see this sort of freeze out occurring of the water, and the pressure required to keep that flow going increases until you basically have a blockage from that impurity, as you might expect. But what's interesting is that if you look at the effectiveness in terms of the reaction of the conversion from ortho to para, you could see that these impurities were causing a problem from the very beginning. 20 hours before you would have seen the sort of onset of the heart attack just from the pressure signal alone. So this tells us we've got a very nice way of checking whether the impurities are present in our hydrogen, and whether they're having a problem, and if we need to intervene sooner rather than later. Because once the blockage forms, you're talking about weeks to fix a large-scale cryogenic system, warm it up, fix it, which is known from the LNG industry. So the final example I want to come to is around how do we lower the cost of making liquid hydrogen. And this is a project that the FIChemE is doing with the University of Melbourne, and Richard, his team is heavily involved, as are others here today, and the UWA team, and with support from ARENA. And what this is showing is the amount of energy required to liquefy a kilogram of hydrogen. Current state of the art is sort of around 13 kilowatt hours per kilogram of hydrogen. That's the thermodynamic limit is just below about 4. And people have talked about, ways in which they could bring that down. And these are all hypothetical, not even demonstrated. They're done in process simulators, but no one knows whether they're real or not. But the basic idea that in the LNG industry, I worked this out a long time ago, is that if you use a mixture as your refrigerant, you can achieve a nicer or closer match between the cooling temperature and the hot temperature, so that the heat transfer efficiency is much, much better. And the other problem with hydrogen is the only refrigerants that you can really use at those low temperatures are very light molecules. So compression is a problem. What we're going to do in this ARENA grant is essentially try a mixed refrigerant for the first time in hydrogen liquefaction. And where you take helium, which is the normal refrigerant, and you put in some neon, so you make nelium. This allows you to tune its composition to match that cooling curve, and it also gives you a larger molecular weight, so that the compression can be done a lot more efficiently. Now, one of the issues is you can't do this at a small scale with simple compressors and expanders, because you can do it, but the data you get aren't representative of what they would require, or what is needed to prove it up at large scale, industrial scale. You really do need to have a turbo expander. So we've essentially finalized the construction of this system, where essentially we'll be testing this mixed refrigerant nelium through a couple of heat exchangers to liquefy a stream of hydrogen. And importantly, it does have a turbo expander therein. Okay, and so we've taken a commercial design that works at about 100 kilograms a day of hydrogen, and we've adapted it to use this nelium. So once we demonstrate that this works, actually we will be at a scale which is already commercial in the market. And this will be demonstrated at the flagship project of the FIChemE, which is called the Kwinana Energy Transformation Hub. So Kwinana is the industrial area south of Perth, about 25 kilometres. And the state government has allocated the CRC about 3 hectares of land. And we're going to be building there 130 kilograms per day of electrolysis. And it'll be coupled into this liquefier shown here in its schematic that and there will also be a lab building on site. And the purpose of this is to do the sorts of larger scale demonstrations that simply can't be done in labs, but are needed to actually allow technologies that we develop in our laboratories to be translated into industry. So no one's taking a risk on a $1 billion plant. Doesn't matter how good your data in your lab is, they need to see it work at a scale that they can trust, and that's the case. So on Wednesday, I was down on site, and that's the current progress of the KEF facility. That'll be where the building goes, and we'll be putting that liquefaction system inside. Well, the liquefaction system outside, but we'll also have systems inside. So, to conclude, the future decarbonised energy systems will definitely need to transport and store hydrogen and CO2 because molecules, moving them is cheaper than moving electrons, and there is no net zero without CO2 transport. Shipping cryogenic liquids is the best way to move molecules overseas. And the LNG supply chain is technically mature and cost efficient, so we should take as much of the lessons that they've learned and use them as our sort of starting point for these new supply chains. In particular, identify differences where CO2 and hydrogen, their specific features require new knowledge, and so we're underway and doing the research to provide those solutions. So with that, thank you very much.